I have to apologize that I don't have your exams to pass back today. I usually... What? I know, I'm a slacker. They're all graded, but we just need to still add up all the points and do all the busy work and put them all in order so I can slide them across the floor and input the scores into Canvas. I did just post and, well, unmute and post the averages for the computer portion of the exam. Okay, so let's just write those up here. So here we have exam 3. The first attempt on the multiple choice was 63.9. You guys had fun with that, I can tell. Second one, though, went up to 90.1, putting us for the average at 76.6. Okay. So I've got to give you kind of, challenging on the first try if you're going to get a 90% average on the second one, right? So that's good. I think that there was one problem that a lot of people didn't get in the end, and all it was a matter of alphabetizing the substituents, right? And I think we talked about that specific scenario in class. In grading we can talk about this later, but in grading the written part, I graded both of the synthesis questions myself, and to be honest, I saw a lot of the mistakes that I warned you that you would make. So we'll say a little bit about that on Wednesday when I pass them back. Okay? Let me just say something about Canvas. In the grade book in Canvas right now, if it shows a percent, all it's doing is adding up all of the points that are in the grade book. Okay? And so it's not really representative of your real standing, because especially what it's doing is it's taking all of what I call the raw scores, all of these scores, and adding them all up and adding that to the total exam score, which I haven't posted for exam 3 yet. But so it's not really representative, and it's, okay, let's quiet down. And I haven't figured out a way to be able to really have a good running total to have that correct all the time, because every assignment, everything we put in changes the relative proportions of each of those different categories. So what I will do in the end is that all of those raw scores will be 0% of your grade, right? Only the total exam scores plus each of the homeworks, which you get to drop 1, and the extra credits. Okay? All right, yeah, so don't, you can go through and add those up and calculate what your percent would be right now. Okay? Any questions? All right. All right, so we're back into a normal week now. We have assignments this week, so they're the week 14 assignments, just started. We're still in chapter 23, but the chapter 24, Learn Smart, is up and available as well. We have SI, UTF, all of those things going on. So remember, if you haven't signed up for a time slot for the final exam, you should do that, because it can fill up at the testing center during finals week. Okay, so just make sure you're... Okay, let's quiet down. Too much talking today. It's too nice outside, I guess. Nobody wants to be in organic chemistry right now. All right, so we are in chapter 23, right? So we are talking about reactions at the alpha position of carbonyl groups. Right? We talked about the enol formation, we talked about the acidity of the alpha position, and then we talked about two main reactions. We talked about, okay, there's still too much talking. The halogenation at the alpha position, and on Friday we talked about alkylation at the alpha position, so putting an alkyl group there. So we have really one more reaction to talk about. It kind of has two parts to it. We'll talk first about what's called the decarboxylation, and then we'll apply that to what these are called the malonic ester and the acetoacetate syntheses. All right, so it's applying what we've already learned and then just adding one more additional thing to it. And then once we make it through that, then I have some fun synthesis problems for us to practice. Okay? Let's do a clicker then if there's no other questions. All right, so here's kind of where we're at as far as our objectives for this chapter. We just finished up the alkylation reaction right here, and so now we're going to aim at doing this malonic ester and acetoacetate syntheses, and we're going to start out by looking at what's actually the last step of these reactions. Is called the decarboxylation step. All right, so here's just a series of reactions. We're either treating these dicarbonyl compounds with acid or base and typically heating them as well. All right, and I think that the outcome is not obvious for looking at this right now. So what we're going to end up getting, let's just look at the products and then we'll go back and see how it happens. Okay, so for this first one up here, we are going to get this ketone. Okay, there's going to be another byproduct. What's the other byproduct, you think? CO2, decarboxylation. So we're losing a CO2. Okay. What about the next one? What do you think we're going to get? No reaction. Okay. The next one, we're doing it in base instead of acid. And we get cyclohexanone plus CO2. The last one, let's use a dicarboxylic acid. And so in this case, we are going to get acetic acid plus CO2. All right, we usually have to heat that one up a little bit higher. Okay, so what's different about the second reaction that it doesn't react as compared to all of the other reactions? Right, that one doesn't have just a single CO2 group between the carbonyl. Right? All of the others have a carboxylic acid with a beta-carbonyl, either a beta-ketone or another carboxylic acid. Okay, and so that's what's going to be important. So let's look at how these actually take. All right, so two examples. Both of them are essentially going to be the same, whether it's this beta-keto acid or the beta-dicarboxylic acid. Okay, the mechanisms are going to be the same. All right, so in the first example, we're treating this compound with hydroxide, so it's under basic conditions. What do you think is going to be the first step of the reaction? Deprotonation. Right? Acid-base chemistry. We got hydroxide, we have a carboxylic acid. The fastest thing that can happen is just acid-base chemistry. All right, so the first thing that happens here is just the hydroxide pulls off the carboxylic acid proton. Okay, we're going to get the the conjugate base, like this, right, in water. And then this is the point at which it's going to decarboxylate, right? And when it's base, and we have this, these are going to be very strongly electron donating. So these electrons can go here, and then they can just go right over to here. And what this is going to give us is this, right? And we're going to lose CO2. Okay, so what's our kind of product that we've formed so far here? What do we call that? It's an anion, carbanion, but it's a special kind, right? It's an enolate, okay? So this is an enolate. Remember, this is in resonance with this structure here, right? And if we have this in base, it's also going to be in water, and then one of these is going to react with water, or we can draw it with either one of them, but let's just use this. It's going to pull off a proton off of water, it reforms hydroxide, and just forms cyclohexanone. Okay? So in this case, so tell me, if you look at this reaction here, and if we made one small change to that structure, like this, and I'm just going to make that conjugate base, do you think this one, if we just heat this up, do you think that one will decarboxylate? No. So why not? What's the difference between these two? I know that carbonyls are one carbon further apart, but as far as the mechanism goes, what's the difference? Yeah.
So I think in the bottom case, if the carboxylate or the carboxylic acid was to leave, that would leave a carbanion that's not resonance stabilized, whereas the other one, that negatively charged carbon will be stabilized.
Exactly right. So what he said, Van said, was that if this goes like this, if this follows the same thing, these electrons are just going to go onto this carbon right here. Let's just draw out what we would get. It would just be, I'll draw out the hydrogens here, CH2 with a carbanion like this. But notice, because these electrons now are separated from the pi bond over here by an sp3 hybridized center, they cannot be stabilized by resonance. Okay? So this one is really very basic and unstable. Very basic and unstable. Right? Whereas this enolate up here is stabilized by resonance. I'm just going to put a little abbreviation there. Okay, so why does that matter? Right, so what role is this carbanion or the enolate up there, essentially what role are they playing in this reaction? No, not a nucleophile, right? They're falling off of the structure, carrying electrons with them. They're acting as leaving group. Right? They're coming off, taking the electrons with us. It's just like a halide coming off, taking the electrons with it. What does it take to be a good or a better leaving group? Usually good leaving groups are Well, they can be electronegative, but what does that make them? They're going to be weak bases, right? Good leaving groups are always the conjugate base of a strong acid, right? And so they're weaker bases. And if we look at this one, this is very basic because there's no resonance stabilizing this one. The enolate up here, on the other hand, is not a great leaving group, but it's better than this, and it's good enough that if this goes at all and CO2 comes off, CO2 is not going to go back on, and so it just drives the reaction to product. Okay? So we have to have this system of these two carbonyls, you know, adjacent, almost adjacent to each other to have a good enough leaving group for this to take place. All right, so let's look at what happens in acidic conditions. All right, so under acidic conditions, the initial step isn't going to really be affected by the acid itself. All I'm going to really do, this isn't really a reaction step, I'm just going to redraw this in a certain way. Okay, so here's this. I'm going to just rotate and aim the carboxylic acid hydrogen up. Okay, and so now I'm going to draw this reaction and going this way. I'm going to take this pi bond and it's going to come up and react with that proton. So we get an intramolecular proton transfer. And it can happen easily like this because it reaches around in a 6-membered ring, which is a very stable ring size. Okay, so then the electrons between the oxygen and hydrogen can come down here, form another pi bond. These electrons, I'll push them all the way over to here, right? And they're pushing around, looks kind of like either resonance in a benzene ring, or if you remember the Diels-Alder reaction, you know, these kind of 6-membered rings. Let's see here what we get if we follow those arrows. Okay, so we got the OH here. We've got a single bond to the oxygen up here, but it's grabbed a hold of the hydrogen. Okay, and then we formed a carbon-carbon pi bond like this. And then our other product, right, is just like this. 2 double bonds to the 2 carbonyls on a single carbon, so carbon dioxide. What do we really have here? How can we describe this compound here? What? What if I put a carbon over here and we just looked at this part here? What would you call it? An enol. Right? So this is an enol of a carboxylic acid. Okay? Because if we move this proton down here, we move this double bond up here, then we get, this goes this way. I'm just going to put like this OH over here, the double bond up like this, and then it's going to be a CH3 over here. Okay, so we essentially get, right here, this is, what acid is this? Acetic acid. Okay? All right, so if we start with a dicarboxylic acid, like this is malonic acid. All right? If it decarboxylates, it gives acetic acid. All right, so let's see some applications of this. Okay, why are we just doing these kind of random structures, right? So let's look at some. Just named as the malonic ester synthesis. So remember the acid that I showed you? I said it was malonic acid. So this is just a diester of that. Okay? So this, you call it dimethylmalonate. All right, so we're going to take this compound and we're going to treat it first with methoxide in methanol. So what's going to happen? treating it with a strong base. We have some acidic protons here in the middle. So we're going to do an acid-base reaction, just like in the alkylation steps. What we're going to do here is we're going to alkylate that center position. And why do I use methoxide specifically? Yeah?
Because it's the same functional group as that ester.
Exactly. So we use methoxide as the base when we have a methyl ester. Because if we get some transesterification going on, we keep the same compound, right? All right, so we're going to deprotonate that. Let's draw out the whole thing here. We're going to deprotonate this. That's kind of doubly resonance stabilized. All right, because the minus charge can be delocalized to both carbonyls, and that reacts in step 2 with the alkyl halide. All right, so we're using bromoethane. We just do an SN2 substitution. Oops, that's not right. CH3. And we've just added an ethyl group at this center position. Okay, we've just done the alkylation. All right, so then what we're going to do is we're going to treat that with acid, and we're going to heat it. All right, so can that compound directly decarboxylate from here? No, but what if we treat an ester with acid and water and we heat it? It does a hydrolysis, right? So it does an acid catalyzed hydrolysis. Okay, so this is the H plus and H2O, and we heat it. This is going to hydrolyze both of the esters. All right, and then in the same step, it's going to decarboxylate. All right, because acid and heat was one of the conditions for decarboxylation. So we're going to lose a CO2, and let's just kind of circle. We're going to lose like a CO2 right here. Doesn't matter which one. And so our product is going to be like this. Oops, I have a little gap there. That's the bond that we made. Okay. I'm going to take out the gap though. All right, so we've made that bond right there. Okay, we don't see the presence of the carbon dioxide in the product though, right? All right, so let's try another one. Look at this other one. It has a list of 5 things that we got to do. It's like, yeah. On the last step, well, you don't have to in this, right? If we were going to, if I asked you to do the mechanism, then you'd have to show how it transfers and everything like that. But if we're doing more of a reaction, predict a product, or predict, or a synthesis or something, you don't have to show that. Okay.
Dr. Jason,
Yeah.
that's a good question. So we still have that other hydrogen at that alpha carbon position?
We do.
Is there another way you could like add, like do it again, like a second round of it? Or?
Oh, good question. Let's work the next problem.
Oh.
Hang, you just are thinking about my own thought process here. All right, so look at this next one. right? We have, if we look at that huge list, we can break it down, right? Notice that the first two steps involve base and then an alkyl halide, okay? The third and fourth steps, base and a different alkyl halide, right? So we're essentially doing two alkylation steps, one after the other. And then the final part is the acid and heat. So that's where we do the hydrolysis and the decarboxylation. Okay? So let's do the first two steps first. Here, let's go down this way. Okay, so after steps, I'm just going to do 1 and 2. Oops. We have added an ethyl group. So this is just like we did right up above there, right? Then we're going to do steps 3 and 4. We just deprotonate. We're going to take off this proton in the middle. There's still one left there. And then we're going to add a methyl group. Okay, so we have a methyl and an ethyl at that center position now. Okay, can we alkylate it again? No, there's no proton on it anymore, so there's nothing to deprotonate, right? We can't make an anion there. So now we're going to treat it with our acid and heat, right? The first step is always going to be the hydrolysis. So we can draw the hydrolysis product here. We've got a methyl still there and an ethyl. And then it's going to decarboxylate, loses CO2, and what are we going to get? We're going to have this. We're going to have a methyl on the alpha position and an ethyl. Yeah, question?
I think we may have gone over this already, but just to make sure, in these types of reactions, we have to be very conscientious of the stoichiometries of our reactants being used?
Yeah, probably.
Okay, so we're just always going to assume one equivalent.
Yeah, we're going to just assume one unless we say more. Yeah. All right, so let's look at what we've accomplished here. And so again, we've lost this CO2, so we can't even see in the product that it was ever even there, right? So if we start with a malonic ester, so we have the same one in both cases, then the part that we're going to end up in our product is essentially this part right here, okay? And that is going to be this part right here, or this part right here. So in essence, what we always end up with is, in this malonic ester synthesis, is a substituted acetic acid. Okay? So the acetic acid part is what we get if we didn't do any alkylations and we just had the malonic acid. That's what I showed you on the slide before. But we can alkylate once or twice at this position and then decarboxylate. So this is the part that if you see something like that, if you see a substituted acetic acid, then you're like, ding, right? I could make that with the malonic ester synthesis. Right? I just know that's how you guys are going to do it. So let's go. We'll go back from there. So here is kind of our retrosynthesis. If we see that, then we'll know immediately that we could make it from a malonic ester. Okay? Any questions? acid there. We could do more chemistry on that as well, right? Okay, so here's another fancy example of this. All right, so in this case, instead of, say, using two equivalents of the same thing, look, we're going to use that dibromo compound. So what is it? 1, 2, 3, 4, 1, 4 dibromobutane. Okay, so this is going to be a case where the reaction can actually continue a second time. All right, so let's just follow this through and see what can happen. Okay, in our first step, I'm not going to show every step of the mechanism. Let's just do this. We're going to deprotonate, and then we're going to alkylate. Okay, notice that I have ethyl esters this time, and so I used ethoxide as the base. Right, we want to match those. So, and I'm going to do a shortcut here. I know they do this in the book sometimes. I'm going to use an ET. This is going to equal ethyl. All right, we're going to just cheat a little. So an ET, so that's an ethoxy group. T, and, oops. Now we've alkylated this once, and so we've got 1, 2, 3, 4, and then we have a bromine on it, and an H. Okay? So now we're going to do the same reaction again. Okay? And what's going to happen then? What kind of compound are we going to get? We're going to get a cyclic compound. Okay, this part is all in. What size of ring are we going to get? Okay, so we have, let's see, let's use this one. Let's just count them. We have 1 carbon. Oops, that's not what I wanted to do. We will have 1 carbon here. 1, 2, 3, 4, 5. Right? So carbon 1 is going to end up bound to carbon 5. And so in this case, we're making a 5-membered ring. Like that. Okay? So then, we're going to do step 3. This time I wrote out hydrochloric acid and water and heat. See if you can draw out what the product of this is going to be. All right, so essentially what we're going to get, we're going to lose a carbon dioxide, right? And so we're essentially going to get this piece right here, right? The ethoxy groups get hydrolyzed off to make the dicarboxylic acid, and then we lose CO2, and so we are going to get this, okay? And we're going to lose our CO2. So again, we started with a malonic ester. We get a substituted acetic acid. All right? Do you see the acetic acid in there? Okay, right? It's this part right here. If we just go right there, if we carve it out like that, there's our acetic acid. Right? And we have 2 alkyl groups, but they're linked together. All right, so we can starting point. Okay, this is called the acetoacetate synthesis, but it's essentially the same thing. The only thing that's different is that on one side here we have this methyl ketone, or we have a ketone on this side, and this is kind of the aceto part for an acetyl group, really, and this is the acetate part from carboxylic acid, so this is called acetoacetate. Okay, so it's going to just follow the same process that we've been doing. Okay, so if we go down here, first two steps, we're going to deprotonate that center position, right, the most acidic position, and then we're going to alkylate. Again, we use methoxide because we have a methyl ester. This time we're adding a butyl group to that center position, like this. Okay, we're going to treat this with acid, aqueous acid and heat, and we're going to, let's draw each step out here, we're going to hydrolyze the ester. All right, and then it will decarboxylate. And so we're going to lose the carbon dioxide from the carboxylic acid side of this. Right, and so our product now will be this, this. All right, and the bond that we formed in the process is this one right here. Okay, so instead of getting a substituted acetic acid as the product, what do we call if we just carved out this piece here? It is a ketone. There's a kind of a common name for that ketone. Acetone, right? So we get a substituted acetone. All right, so if we see a substituted acetone, we'll be like, ah, yes, acetoacetate synthesis, right? All right, let's try it one more time. See if you can just go straight to the final product in this bottom one. Okay, so again, remember we want to keep this part here. This is the acetone piece. And on one of those carbons of the acetone, this benzyl group is going to be attached. So if we just go to our final product, here's our acetone. Then I'm going to add a benzyl group onto there. Okay? So we made this bond right here. So it's a substituted acetone. Okay? We could also, just like we did before, we could do this one time. We could do 2 alkylations. We could make a ring. We could do all the same stuff as we did with the malonic ester synthesis. So in this case, what we want to look for is if we have some product that you could recognize a component like this, right? So a substituted acetone, then you could imagine making this from the acetoacetate. Okay? It's just analogous to the malonic ester. We just took an ester off of this side and put an alkyl group. Okay? This could be a longer alkyl group too. It wouldn't be called acetoacetate, but it could be some other alkyl group, and you could still do the same chemistry. Okay, because that's really just being carried along. All right. The thing that we have to do here is to apply some of what we learned, and we don't really have enough time to do all of this right now. I'll have to look, and hopefully we'll finish up on Wednesday doing some of this. Maybe think about this for just a second. We have 3.5 minutes. That's all it takes to do a synthesis like this anyway, right? And then we'll be going on into chapter 24. Oh, I thought we were still working here. Huh? I can end if I want? Dang, I just want to keep going. I can also keep going longer if I want then. All right, let's just start this out. Let's what can we do to a cyclohexane? We've got no functional groups on it at all. How can we put a functional group on it so we can do something to it? We can just brominate it, right? Okay, we're just going to do the first two steps here. So bromine and either H-nu and heat or something like that, right? So this is going to brominate it. All right? But in the end, we kind of, well, now let's just stop there. Think about if you're so inclined, think a little bit about this on how you could get two alkyl groups onto this. All right? I'm sure you'll spend all your time between now and Wednesday. Okay, I'll see you on Wednesday, and I'll have the exams for you then.